and gentlemen. With climate potentially changing, and we're not talking about day to day, but we're talking about over year to year, if we notice climate begins to change, and maybe areas are colder than they once were, maybe there's more precipitation than usual. As the climate changes and our areas where we live potentially change with it, we have to recognize the fact that certain species may have trouble adapting, humans or wildlife. That last beautiful animation was brought to you by Wisconsin Public Television. And we have this new one. This shows some good examples of potential examples of climate change that our country is faced with. And this is brought to you by Vice News. The idea is that science is working right now to study data to try to determine how scientists can connect the kind of extreme weather we see with what people are calling climate change. And let's look at some of the different kind of visual ideas of what they're doing. So we have forest fires, and we have potential droughts. The idea is that science is always trying to compare and connect the weather we're noticing and extreme examples of weather to climate change. As we study climate change and as we study the possible effects of human-caused climate change, as scientists continue more and more to try to connect weather and climate, they also need to be aware of how species respond. And we're always, in our class, in our biology class, we always want to know how species might be responding to climate change. This brief video from the Washington Post is suggesting that we're currently entering a sixth mass extinction due to things like climate change. So they're noticing that humans are potentially to blame for these extinctions. And a bunch of scientists got together with the Academy Science Journal, and they noticed that lots of populations are declining. They're going down. They studied almost 28,000 species. Examples are mammals, birds, reptiles, amphibians, all across the world. And they found that 30% of them are losing populations. That's roughly over 8,000 species potentially might be going extinct due to climate change or humans changing habitat. So here in our notes, the last scientific problem we were trying to do was, how do scientists know when an ecosystem is in trouble? How does a scientist know when a species might be going extinct? So we want to focus on this problem right here. What are scientists doing when they think an environment might be having a problem? And so last video, we went through this process of reviewing random sampling, which is an activity we do in class, where scientists can estimate a population, such as these poppies, without counting every single one of them. So it's a way to know how many are growing out here without counting all of them, because that takes too long. In the end, if this whole lab is done correctly in class, you're going to get these four values. You're going to get an average number of flowers per grid, and grid means just per little section in the field. Remember, this represents a whole field. You're also going to be able to estimate how many flowers are in the field without counting all. Remember, the estimate is a way to closely guess the population. And then you actually took the time to count every single little dot or flower in the field. And then in the end, we have this thing called percent error. And that's where our last slides left you. So this is slide 21. And in slide 21, we wrote down the definition for percent error. But I have a feeling you might want me to help you calculate percent error for slide 21. So if you haven't yet, please pause the video, write slide 21 in your notes, and copy down percent error, including the formula or the little equation for solving percent error. So as professors, college students, and biology students go and attempt to investigate populations, such as these Bristol students, which I believe are an English group of students, as they collect data on species, they need to know how well they've estimated a true population. They need to know their percent error. Same for this group of people. They are working in the field. They are collecting different species with nets, and they're trying to estimate a population. But they ultimately don't want a high percent error. They want to know how many of a species there are in nature. They want a low percent error so that they know if the populations are getting close to extinction or not. So in your notes, you should have this definition for percent error down now, and then we're going to answer A and B. So in your notebook, please write A, and then we're going to set up this equation. So what you're going to need to do is the estimated. So A says, I thought 70 people would turn up to the concert, but in fact 80 did. So we're going to calculate the percent error for this person who thought 70 would show up to the concert, but 80 did. So the estimated amount was 70. So we're going to take 70, and it would go right here at the estimated value. Boom. But the exact value was 80, so we're going to put 80 for exact. And then the exact value again is 80, right? It's because 80 people actually showed up. So the calculation is 70 minus 80. So you're going to calculate 70 minus 80, and then you're going to divide it by 80, and then multiply it by 100. All right, so 70 minus 80 equals negative 10 divided by the exact number, which was 80, equals 0.125, but we have to multiply it by 100, so times 100 equals 12.5. Notice the number is negative. When we do this in class, you can ignore the negative, or you can use it. The negative means that this person underestimated. They thought less people would show up than really did. So the negative says that they thought there was 12.5% less people than there actually was. So this is a 12.5% error. This person was 12.5% off from the true actual number. All right, number B is, let's calculate B. We have a plate full of tomas, and let's estimate how many we think. So I'm going to estimate that there is, in fact, I'm going to pretend that there is 25. If I can grab it. So let's predict that there is 25 tomas on the plate, and we're going to subtract it from the actual number, which is, there's actually 40 on there. Yes, I actually counted all of them. So we predicted that there was 25, but then we counted them all and found out there's actually 40. And then we need to put the exact number again as the denominator. We get our calculator out, and it's 25, which is the estimated, minus the exact number, and that's 40. So minus 40 equals 15. Notice it's negative, so we underestimated. We thought there was less than there actually was. So we have, So we have 15 negative divided by the exact number, so there's actually 40, equals 0.375. Now, then we have to multiply that number by 100, so times, and this time I'm going to multiply by a negative 100 just so that number comes out positive, because it's supposed to be an exact value when you do the fraction. So in this case, I underestimated and had a percent error of 37.5%. That's kind of high. If Grandma made these dolmas, she would not want to hear that I was 37.5% incorrect on how many she made, because she put a lot of time into those, and she wants you to eat them and share them equally. So in your notebook, make sure you have the definition, and you've done the 2 calculations with me in your notebook. So make sure you wrote this formula out and calculated it just like I did. And if you get confused, just pause and rewind this video to see how I did it. But I want you to show the math for A and B for slide 21. All right, so over the next maybe 10 slides, we're going to be spending more time learning about these problems now. How does competition lead to stress? So when you have a bunch of different individuals competing for food, or if you have a bunch of people competing to go on dates, like at this beach, how does it lead to stress? And the next thing is when you have a population of organisms, how are they spreading disease? When you have people living so close or densely, what can we do as people to try to protect ourselves from the spread of disease and other things that can harm and reduce our population and make us sick as an individual? So really, over the next 10-15 slides, we'll be spending and trying to learn more about this. So keep up with me, and let's see if we can't unravel some of these little mysteries or scientific problems. All right, slide 23 is pretty cool. Slide 23 graphic. I'm going to put it up to full screen just for a short period of time, just so you can see the graphic better. Before I do that, though, you need to, in your notebook, write slide 23. So in your notes, pause it and write slide 23. And then there's going to be 2 questions, 1 and 2. So in your notebook, please write 1 and 2. And I'm going to help you answer these questions by making the screen a little bigger, okay? So here we go. So the screen's a little bigger. What I'd like you to do right now is just go ahead and pause this video and try to take in what it's showing you. What is the information in this? What does the top number mean? What does the bottom number mean? Because each one of these bubbles represents a country, and you have a top number and a bottom. If you go to US or China, it'll explain what the top number and the bottom number means. So please, right now, think about the questions you're answering for slide 23, and please interpret and figure out what these numbers represent. All right, so if you haven't figured it out already, this map is showing you how many people in that country live in the city, and what percent of the population are city livers. So if you look at China, they have 559 million people, but less than half live in cities at the time of this document. So this document is old now. So this isn't up to date. This is probably from mid-2000s. And then you have the U.S. has 246 million people living in cities. That's 81% of our population. So most of our people in our country live in the cities or urban. It says, what's the human population in the urban area of LA? It's this black bubble. There you go. That's how many million. Write it in your notebook for slide 23. All right. Question number 2, it says, is China more urban than the U.S.? Compare the percentages. Our percent is 81% urban. They are 42% urban at the time of this infographic made. Also at the time, our world population was 3.3 billion. It's a lot more now. Our population is growing, growing, growing. Now, as we think about people living in the city, we need to think about population density. So we're pretty much done with this slide. You should have 1 and 2 done now. Let's move on. And let's think about population. Let's see how people have increased in density over the city of LA. So you decide, are more and more people moving to the city of Los Angeles? This is since 1900. Look at the population grow. People from all over the world are moving to the city of Los Angeles, or our general area that we call home. Look at that. Each bubble or each dot represents a high density of people living very closely together. So population density, it means when people, it's based on how many people live in a certain area, how closely people live together. So how crowded is it? So you have urban versus rural. So people are high density in the city. People live very close together, much more crowded in the city. And we have more people moving to the cities. So less and less people are living out in the country. And you've already decided that a lot of people would prefer to live out in the country where you're more spread out, lower density. And the city, we're more crowded, high density. Gentlemen, this is slide 24 in your notebook. Please write slide 24. And let's get this definition out. Let's just go ahead and pause it and get this down for slide 24. So this says that a population, when it's shaped as a J, so when a population grows and over time grows really quickly and they start making lots of babies. So this is a growing population. Notice it makes the shape of a J. When a population grows in the shape of a J, so if you graph out how many individuals, the size of the population over time, and it takes the shape of a J, that means the population is growing exponentially. That's called exponential growth. All right, the next thing to do for slide 24 is to draw this graph. So you need to have the y-axis, population size, go for 100, 500, 1,000, and you need the x-axis to show time, or the horizontal axis to show time, and the vertical axis goes up to 1,000. The vertical axis is population size. All right, the next thing you need to do is just make sure that you draw this J-shaped exponential growth line right here. And then number 2, it says pick a new species to represent the population. So you're just going to draw something here other than flies. Be creative and add any new animal, anything fun that would represent what you're saying is the population there. I was created and I decided that this population J-shaped growth would be meeseeks. So I drew in some meeseeks. All right, ladies and gentlemen, don't panic. The next video will help you finish slide 24. Have a great day.